In
and
July.
It was nice. Yeah, in July, it's true, until the end of July. And well, we are very happy to receive you, even if just virtually. And you are going to talk about the universality of multi-component stochastic systems. So thank you very much for your for accepting this invitation.
Okay, thank you for the invitation. So it's been a while. I haven't done a talk online, so I don't know if I'm gonna succeed. I haven't got used to the pandemic mode. So what I will discuss today is a joint work with Patricia, Giuseppe Cannizzato, and Riccardo Misturini. So let's start with, given the audience and given the series of seminars that you already had, I guess that I can allow myself to, let's say, skip. I cannot move. Okay, skip a few details about the models and already known results. But if you need, I mean, if something important is missing, you can stop me and ask questions to fill the gaps. So the general model that I will discuss here is the simple exclusion process that you all know very well. So I guess that I don't, okay, it's a particle system, so an exclusion process with particles. In this case, we consider the model, the process on the discrete torus. So here I represented it with a line because for convenience, but I guess you can zoom in. If you zoom in enough, you can approximate with a line. So you have particles on each side. You can either have a hole or a particle, and this particle they place with left and right neighboring jumps with a certain probability. And according to the value of these jump rates, you can have different models associated with different large time behaviors, and so different statistics. So in general, for this, we consider a model where the density of particles is conserved. So the total number of particles on the torus is fixed. And you can characterize the invariant measures for the model, which are Bernoulli product measure of a parameter that we call rho, which identifies the density of the particles. This is a very important aspect for what we will discuss later. So in general, for this model, we are interested in characterizing the large time behavior. So meaning that we want to derive with a very well-established technique the PDEs or the stochastic PDEs that describe the space-time evolution of the particle densities. So their deterministic evolution and their fluctuations around their deterministic trajectory. So in this talk, I will discuss how the main focus is are the equilibrium fluctuations. So the fluctuation for the model related to SEP, so the simple exclusion process, when we start from a configuration from a Bernoulli measure. And so regarding fluctuations, you can, for SEP, you can observe different statistics or different behaviors. You can even observe in the limit a diffusive or a super diffusive behavior, and we will see in the next slide more about this. So let's say that we consider the model where we can the asymmetry. So in the weakly asymmetric regime, meaning that the asymmetry is scaled as 1 over n to the certain power gamma. So what happens is that according to the strength of the asymmetry, we will observe different behaviors. And this behavior, so these large-scale statistics, are said to be universal in the sense that these statistics that characterize the behavior, the last time behavior of this model can be obtained from a variety of different microscopic models, and so they are universal in the sense that they do not, the limit that you obtain does not depend on the details of the underlying microscopic model. So how do you characterize universality for the process? So in general, you consider a stochastic process of time and space, which describes your quantity of interest. For the, let's say, historical reason related to the community of the cardinal-partisan community, we call this object height function. So, and what you do is you consider a set of exponents. Here they are denoted with the parameters R and Z, and you consider the space-time denormalization of your stochastic process. And so you characterize the universality class as the, so you define this operator R epsilon, and you define the universality class as the Bayesian of accretion of the limit for the parameter, the scaling parameter epsilon going to 0 under this operation of the scaling dot epsilon, epsilon. So what happens for SEP, but in general for one component systems, meaning that for the models where you have one conserved quantity, is that when you look at the fluctuations of this object, you can either observe a diffusive behavior if you consider the scaling with exponent 1 to 4, defined by this relation here. So this means that you are in the Edward-Wilkinson, the so-called Edward-Wilkinson class, so characterized by Gaussian statistics, or you can have a super diffusive behavior under the famous KPZ or 1 to 3 scaling. So it means that you are in the KPZ class, where the statistics are no longer Gaussian, but they are characterized by a distribution observed in a random matrix theory called the GOE Tracy-Widom. So the connection between these two classes is has been known since 2009, 2010, and it is represented by the KPZ equation, or its relative, the Stochastic Burgers equation that are here depicted, meaning that it was proved that the KPZ equation has GOE statistics for large times under the KPZ scaling. And it shows Gaussian statistic, meaning that it converges to the additive stochastic heat equation for short times under the 1 to 4 scaling. So this is, let's say, very well established, and there is, according to the possible behavior that you can observe, there is all that you can say. But what happens, what we are interested in here in discussing is to see what happens when you consider multi-component systems. So meaning that you can have many conserved quantities that here we indicated with this vector rho. So here we have m conserved quantities. For example, here I depicted a completely arbitrary particle system with different species that are indicated by different colors, and where you observe the difference of in the dynamics, because the jump rates, so in this case, instead of having simply one particle that jumps to the right or to the left, you really have particle exchanges between neighboring sides. So the jump rates depend on the species involved. So, for example, these two particles here to the left jump with different rates with respect to these golden and light cyan, light blue particles. So, so what we saw before is that you can characterize a universality class by a set of exponents, and also by the distribution, so the scaling functions that characterize the large scale fluctuations. So what happens here is that what happens for a multi-component system is that the scenario is much richer, in the sense that you can observe more behaviors than the Gaussian and the diffusive and the super diffusive. So how? So you have a full family of new universality classes that appears. So how can you give a guess of which will be the large time behavior, the large scale behavior for this model? So
may I ask a question?
yes.
So when you're talking about macroscopic fluctuations, these are fluctuations around equilibrium, right?
Yes. Here we always around equilibrium.
So okay. So your C's are chosen specifically so that you can compute some equilibrium measure, or because it doesn't seem very okay. It seems a hard problem to compute the equilibrium measure in general, right?
Yes, in general it is when you consider exclusion process. So yeah, it is a problem. For example, the model that we'll discuss later, we chose a slight modification of the model to have a Bernoulli product measure as invariant measure, and that really simplifies the computations. But actually, well, you can actually start from a non-product measure. I think we started to compute to do computation for the model which has a Gibbs invariant measure, and you can modify a bit your proof to accommodate different measures that are not product. But the existence of the explicit form of the invariant measure here is crucial. So this will be everything at the equilibrium. So there will be nothing about non-equilibrium. Okay. Going back to universality classes. So one technique to guess the large scale behavior in which universality class you might fall in is an approach that was proposed by Spohn in 2014, which is called the nonlinear fluctuating hydrodynamic theory. So, and the goal of this technique is to propose a system of stochastic PDEs that describe the evolution of the multi-conserved quantities, starting from the density current relation of the model analyzed. So I will explain this in more details. So what is how do you guess the dynamic the universal behavior? So the starting point is the hydrodynamic scenario in the strong asymmetric regime. So in this case, corresponds, we had an asymmetry of 1 over n to the gamma. We take gamma equal to 0. So the hydrodynamic equation for the quantities of interest in this case will be given by a system of conservation laws. Here we denote with J the vector of the instantaneous current for each component. So what you do is you express the equation by writing the current as a function of the vector also of the vector of the conserved quantities, and so you arrive at this equation, where here J is the current Jacobian. So what Spohn claimed was that if you want to capture the effect of fluctuations, you have to add a phenomenological diffusion matrix and a stochastic term. So in this case, a white noise. So you had this diffusion term and a vector of white noises, independent. And then, what you do afterward is to expand the local density. Local densities around their long time stationary values. So here you can recognize in Y alpha so this Y alpha would be the fluctuation field. So what you can observe. So this is there are some justification for this that I don't really know in details, but you can show that there are by some renormalization group considerations that all the non-linearities of order greater than 3 are irrelevant. So it is sufficient to expand your field around to the second order. And then once you do this, you obtain that your fluctuation field Y satisfy a system of coupled noisy Burgers equation. So this, can you see my pointer? So we are at point 4. And now it is, sorry, I'm still having, so, and now what you do is, so you observe that it is convenient to, since you want to characterize independently the evolution of your fields, it is convenient to transform your field into normal modes, meaning that you take you transform the fluctuation field via the transformation given by the diagonalizing matrix of the current Jacobian, and you arrive at the formulation of the SPD of the SPDs in terms of this phi alpha, which are written in. Sorry, I forgot to say that here the H is the Hessian of the current. So, and now you can reformulate this equation in terms of new quantities. So you have this G alpha, there are new matrices, this D tilde and B tilde are simply the transform matrices of D and B, the matrix and the vector D and B. And these G alpha are the key elements of your analysis. So these are called the mode coupling matrices. And from them, you can extract all the information that you need to know about your Universality class. Just a small observation. So here you see that in this equation, it appears this drift term, B alpha phi alpha. And this already suggests that you have to manipulate a bit your fields to observe a reasonable behavior. So in this case, this term suggests that you already have to take your field in a moving frame with a set velocity given by V alpha. So where V alphas are the eigenvalues of the current Jacobian. Okay. So the quantities of interest that are the ones that together with the dynamical exponent characterize the universality classes are the dynamical structure functions, which are the stationary two-time correlation of the normal modes. So they measure the density fluctuation in the stationary state. So so in this case, we will analyze models that fall into the strictly hyperbolic hypothesis. So meaning that all the eigenvalues are different. So in this case, what you observe is that so the interaction terms, the interaction between modes are very weak. So you can claim, so you can show that, well, we will show it, but you can justify the fact that the off-diagonal terms of this S alpha beta decay very quickly for the large time and long distances. So they are negligible when it comes to describe the large time behavior of your modes. So, and in this case, under this hypothesis, only the diagonal terms will be relevant. And what it is expected is that these diagonal elements will have a scaling form, here represented, with dynamical exponents Z alpha, which can be different for each mode, for all the modes, and a certain universal scaling function, F alpha. And there are these two objects, so the scaling function and the dynamical exponents, that characterize the universality class, and that can be evaluated using mode coupling matrices. So how you can obtain the scaling function, and it's well, it's kind of an involved topic. So I will not give you the details because I also want to discuss the model later. So I will not give you the details of how you can characterize this F alpha from the mode coupling matrices. But I will present, let's say, a possible scenarios of universality classes that you can have in some particular cases. So, but okay, in general, what you can say is that if you consider systems with a short range interaction, so for example, like in the case of the simple exclusion process with multiple species, you can observe an infinite family of universality classes whose exponents are given by ratios of neighboring Fibonacci numbers. So you begin at Z1 equal 2, and then you will this will be followed by 3/2, 5/3, 8/5, etc. And you can also observe here I forgot to write it, but you can also observe the limit value. So you can observe an exponent given by the golden mean. So 1 plus square root of 5 divided by 2. So, and this is what happens when you have two conserved quantities. So the model that I will introduce will be focused on this case. So what happens? So the behavior. So let me explain what happened in this table. So here you have two mode coupling matrices, G1 and G2. And here we denote it with different symbols, the diagonal entries. So we neglect the off diagonal because they are irrelevant. So you can even have so if you have a bullet, this will denote a non-zero entry. If you have a star, this is an arbitrary entry. So either 0 or non-zero. So, and what you observe here is that the large scale behavior depends on the diagonal entries of the mode coupling matrices. And what you can observe when you have two conserved quantities are 5 different behaviors. So, no, actually 6. So you can either have so if the diagonal entries are 0, or if the self-coupling entries. So for example, the entry 1, 1 of the mode coupling matrix 1 of the entries 2, 2 of the mode coupling matrix 2 are 0. You can have you observe usually diffusive behavior, so which is denoted by D. So you're an individual Wilkinson class. And this is what you already saw for SEP. If the self-coupling matrices are non-zero, then you can have you can observe KPZ behavior. So you have a super diffusive behavior. So you are in the KPZ universality class, or you can even have you can either observe a behavior which is which is called sort of a modified KPZ class. So in the sense that you have the same exponent, the same dynamical exponent, but the scaling function is not the same as the one in the KPZ universality class. So it's not the distribution defined by Prahofer-Spohn. And then you can observe two different super diffusive behaviors characterized by Z alpha stable Levy distribution. So the scaling function is given by Z alpha stable Levy distribution with exponent 3/2 or 5/3. And then you can also observe another universality class with dynamical exponent given by the golden mean. So you still have a scaling function, a phi stable Levy distribution. Okay, so just to summarize this nonlinear fluctuating hydrodynamic approach, the approach of nonlinear fluctuating hydrodynamic theory, is that basically when you want to investigate the dynamical universality classes, you have reasonable assumption to say that those can be inferred, the information about the classes can be inferred from the structure of this mode coupling theory, which are determined by simply by the stationary density current relation for the conserved quantities analyzed. Okay, of course this is true only if you consider a system with a short range interaction. So if you look at long jumps or a system far from the equilibrium, so when you can observe long range order in the stationary state, things are not clear. You can observe complex velocities, so all of these will fail. So now I would like to present a model where we apply this technique to observe a transition between two universality classes. So the model is a modification, is a version of the ABC model, which was a model introduced by Evans in the 90s, which is the first generalization of the simple exclusion process. So we still consider the model on the discrete torus. But in this case, instead of having particle holes on each side, we have three species of particles. So each side is occupied by either a particle of species that we denote A, or a particle of species B, or a particle of species C. If you prefer, you can still think of this model as a two-species model, where the particles C's represent whole. And we look at this. Also in this case, the total number of particles of species A, B, and C are conserved. So the densities for the rho A, rho B, and rho C are conserved. And you can still characterize the invariant measure as a product measure, where at each site the probability of having a particle of species A, B, or C is rho A, rho B, or rho C. So here, wherever there will be an alpha, this means that alpha is either A, B, or C. And so we look at this model at the dynamics in the weakly asymmetric regime, meaning that particle exchanges will occur with a rate given by 1 plus and then a term which is proportional to 1 over n to the gamma. For gamma, a parameter between 0 and 1. And these parameters that regulate the asymmetry will depend on the species of particles involved. So for example, a particle of species AB will swap with probability 1 plus EA minus EB divided by 2 n gamma. And the same particle of species BA will swap with probability 1 plus EB minus EA divided by 2 n to the gamma, and so on. And so for this model, it is interesting to analyze three cases. So the first one is when all the parameters EA, EB, and EC that regulate the asymmetry of the swaps between the particle exchange between different species are arbitrary. So, but then there are also two cases where you say, okay, instead of we leave the asymmetry only for particle of species between particle of species B and C, and then we let particle A and B to exchange with rate 1. So, and this happens if we take EA equal to EB. And then we do the same for particle of species BC. So we leave particle AC to exchange with asymmetric rates, and we let particle B and C exchange with rate 1. Okay. So, so for the form of the dynamics here, so here we have two conserved quantities, so we should fall somehow in this table. But what happens here is that for the form of the dynamics, what you observe here is that the non-self-coupling entries, so meaning that of the mode coupling matrices, meaning that for the G1 the entry is 2, 2, and for G2 the entry 1, 1, these are 0. So if you go back to this table, well, you see that the only possibilities that you have is to observe either KPZ, so a combination of KPZ and KPZ for both quantities, or KPZ diffusive, so diffusive KPZ, or KPZ diffusive, or diffusive diffusive. So we obtain this table, and of course you have diffusive for for a certain quantity if the mode coupling matrix associated has self-coupling entry 0. And so of course, if the self-coupling entry is 0, this depends on the parameters that regulate the asymmetry of jumps. So this in our case, the mode coupling matrices will be, the entries of the mode coupling matrices will be function of these parameters EA, EB, and EC. So we have 3 subcases that we studied. So in the first case, so when EA equals to EB, we expect the quantity associated to the density of particles A to be well, not exactly. Let's formulate it this way, but then we will see that it's not exactly what I mean. So the behavior of the first quantity of interest is KPZ, so we expect to be diffusive behavior, and the behavior for the second quantity of interest would be diffusive. And the same if we consider if we impose that EB to be equal to EC, and then if we take non-arbitrary parameters, we will observe both quantities will show KPZ behavior. Okay, so concretely, what are we looking at for this model? So we are looking at the fluctuations of the density field. So I assume that you all of you have seen the definition of the density fluctuation field before. So here we do exactly the same, but we look at exactly the same object for SEP. So I'm 1 over square root average of the occupation variable, the centered occupation variable, but we have to do it for each species. So we have a vector of density fluctuation fields, YA, YB, and YC. And here we have to generalize the definition by introducing a new occupation variable. So if for SEP, it is sufficient to define an occupation variable that on each side has either the value 1 or 0 if there is a particle or not. Here you have to take into account the fact that you have different species. So we define this psi alpha x, which is a function of the configuration of the particle configuration eta, which gives you, so for each alpha you have to define a different function, a different occupation number. So for example, psi ax would be 1 if on site x there is a particle of species A, and it's 0 if there is a particle of species B or C, and the same for psi b or psi c. And so what we analyze is the evolution of this fluctuation field for A, B, and C. So already it's pretty, I mean, it's reasonable to expect that since the particle exchange between two species depend on involve all the species of particles, that there will be some term that will I mean, that the contribution of all the fields will appear when you look at the evolution of a single field. For example, in YA, you will see that there will be terms depending on B and C. And so for this one that will be clear later, we have to we will consider the following object. So this is so we are analyzing. So we are the base of our analysis is the nonlinear fluctuating hydrodynamic theory, and so the objects that we analyze are the normal modes of this system, which correspond in our case to a certain linear combination of the linear combinations of the density field for the species A and B. So as I said, C can be interpreted as a whole. So you can always recover the evolution of C starting from the evolution of A and B. So we will focus only on YA and YB. And so now, according to the hypothesis that we make on the rays, we have three couples of normal modes. So three couples of fields that we analyze. So the first two cases, let's say, are simpler to identify. So you have either the difference of the sum of the fields, or in the second case, you have YA plus 2YB, or simply the field YA. In the third case, you have you still have a linear combination, but the coefficients are a bit more involved. But what's important is that all these coefficients will depend on they depend explicitly on the parameters EA, EB, and EC. And what you have to do, so as it was suggested when I discussed the approach of the nonlinear fluctuating hydrodynamics, is that you have to take your fields in a certain moving frame. And here, in fact, how we define these fields by introducing this translation operator with different velocities for each mode. So in this case, we were, let's say, lucky because for both, for example, if you analyze the first case, Z plus, so both YA and YB have the same, are in the same frame. But given the strictly hyperbolic hypothesis, the velocities for Z minus so the velocities for Z minus is different. So in the same linear combination, you have the same translation operator, but in the other mode, you have a different velocity. So in this case, V minus. And all of these, also the V plus and minus, so the different eigenvalues of the Jacobian for these dynamics, are explicit and written in terms of these parameters EA, EB, and EC. So how do we define? So let's say the goal is to prove the weak convergence of these fields to a certain stochastic processes. So in particular, we want to prove that in the most general case, they will converge to a solution of the Stochastic Burgers equation. And just to, let's say, to give a complete picture, let me say a couple of words about what kind of solution we are looking for. It's kind of a technical slide, so if you know about this notion of solution, you already know everything. If you don't, there is a question. Sorry, that was not for me. So if you don't, it doesn't matter. It's just to give a, let's say, a complete picture. So so what happened is that here, so when you have to prove convergence, in this case, weak convergence of a stochastic process to the Stochastic Burgers equation, you have to be very careful because the equation has some issues due to the nonlinearity. So this the second term to the right hand side. Because you expect that the stationary solution behave as distribution, so squaring the distribution is not an allowed operation. And so what you have to do is you have to show, to justify the limit when you. And so the notion of a solution proposed here is the energy solution that was proposed by Milton and Patricia, and then reproposed in a different form to adjust the uniqueness of the solution by Gubinelli-Perkowski. And so I will not go into the details of all the definition, but the general idea is that you want to, let's say, find the regularization of the nonlinear term in time to extract some bounds on the space-time variance of the nonlinear term. So what you do is you try to interpret the nonlinear term as the limit of a process which is obtained as an approximation of a nonlinear term in a martingale problem. So the starting point of the analysis is always so we are looking at the weak convergence, so we look at the equation in a weak form. So we start from a martingale problem, and so we define this. So one defines starting from a stochastic process, you define the nonlinear term as the limit in epsilon of the integral in time and in space of your process convoluted with an approximation of the identity. And so you can prove that if you have a certain bound, certain control in time, so your process satisfies a certain energy estimate, which is given here below, and it satisfies a martingale problem associated to the stochastic Burgers equation, then the limit in L2 of this approximation exists, and it is independent of the approximation. And so this is the framework where we are working in. So this is the main result. So finally, a lot of words to say that. So we consider these sequences of processes given by corresponding to the normal modes of your system, and what you want to show is that you want to prove the weak convergence to the energy solutions of the stochastic Burgers equation. But so this would be you want to prove the convergence to uncorrelated solutions. So in the limit form, there would be no coupling terms. So there will be no dependence with respect to other fields. And what you observe, you can distinguish the different cases that we analyzed before. So if you assume any condition on one of the two conditions on the parameter of the symmetrical parameters, you can show that one of the modes converges to the Ornstein-Uhlenbeck equation, meaning that you take the stochastic Burgers and you take lambda equal to 0. And the other mode will converge to the stochastic Burgers. While in the most general case, we will have a system of two uncorrelated stochastic Burgers equations. And again, all these parameters in front of the nonlinear term and in front of the noise will depend explicitly on the asymmetry rates. So on the parameters EA, EB, and EC. Okay, so maybe I have time to give not too much, but I will give some elements of the proof. It will be quite fast because the strategy, so the frame of the proof is quite standard. So it always relies on martingale representation of the dynamics, so on Dinkin's formula. But there are some novelties in some technical novelties that we had to introduce to adjust the problems that appear in this model for the correlated fields. So okay, so we start from describing the analysis of the dynamics of the processes in terms of a generator. So which is speeded up with a certain rate n to the a, and so here you have the standard form of the generator of a Markov process, where the rates Cx are given in this more general form. This is just a slightly more complicated way to say that if there is particles of species alpha beta, well, the rate here is 1 plus E alpha minus E beta over 2n to the gamma. It's just to generalize the SEP, the rates of WASEP, so the Euclidean symmetric simple exclusion process. And then, okay, this is we are analyzing the density fluctuation field, this Y and alpha. So the starting point is always the Dynkin's formula, so you can express the evolution of your system in terms of a martingale, and you apply Dynkin's formula to the quantity of interest, so the fluctuation field. And then let's give a look at this formula. So what you see is that basically the only unknown term here is the action of the generator on the field. But due to the linearity, basically what's missing, so here you have a constant, and here what's missing is the action of generator on the occupation variable psi alpha x. So the system is gradient, meaning that you can express the action of the generator as a difference of microscopic currents. So here what you have to do is to explicit this microscopic current. So here I introduced this psi alpha bar to say that it's the centered variable, so psi alpha minus rho alpha. So for example, if you analyze the case alpha equal A, so the microscopic current on the bond x plus 1 is as this form. And here, if you have some familiarity with this sort of techniques, you already recognize some nice term, but also some problems. So okay, so you plug in the microscopic current after integration by parts in Dynkin's formula, and you obtain an equation of this form. This is a very general, so you obtain different terms that will describe the different terms in the current. So let's analyze one by one the terms. So the first term is the psi a x minus psi a x plus 1, is the one that gives rise to the Laplacian. So far so good. Then you have a term which degree 2 term, which includes all the products of two occupation variables that are either psi a or psi a psi b. And then you have the last term, which is the nasty one, which includes this degree 1 term, so in psi a and psi b. And then you have the time derivative of the field. So why do I say that this is the nasty? So what are the problems? So the first problem is obviously the fact that you want to obtain you want to take a large scale limit of this equation, but the equation is not only in terms of A, of the species A. So you already have the problem by the fact that you have product terms of different species. And then, well, if you go to analyze the details of Dynkin's formula, you see that when you take this term in the green box, when you try to rewrite them in terms of the density field, you will see that when you take the n to infinity limit, this term will diverge. So two things to do. The two things to do are to get rid of this green box and to try to express this product of occupation variables in terms of known fields. So how do we do this? So the nonlinear fluctuating hydrodynamic theory gives us the answer, in the sense that so the first thing to do is we define our field by introducing a translation operator. So we look at our fields in a moving frame with velocities given exactly by the velocities postulated by the analysis of the mode coupling matrices. So we introduce this translation operator, and then we look. So if we look at a single field YA, for example, okay, we introduce with a suitable choice of the velocity, we can get rid of this psi A term, but then we still have a term in psi B. So what we have to do is to introduce, to look not only at a single field in A or B, but to look at linear combinations of these two fields. And these linear combinations are given exactly by the normal modes proposed by the nonlinear fluctuating hydrodynamic theory. So once you do this, you rewrite Jenkins' formula for this new field that we call Z, so the linear combination, where each field is in a moving frame. And then you observe that once you introduce this, well, if you apply the time derivative to this Z field, you have a term of this form. So something which is proportional to psi A and psi B. And this already suggests you that one problem is going to be fixed. So the diverging term is going to be compensated in some sense. In fact, if you take for a certain choice of the velocity, meaning that when we are in the case where we speed up in the diffusive scaling, so we speed up the generator by a term n square, and then we take the translation operator of the form v n square t, so we move with velocity v n square, and then we choose the v alpha of the order of the asymmetry, so of the order 1 over n to the gamma. Then this the diverging term and the terms produced by the time derivative will compensate exactly. Of course, by suitable choice of A1 and A2. But these are given by the mode coupling matrices. Okay, so the second thing to do is to rewrite these new nonlinear terms here that I recall B tilde, that will depend on AB in terms of a known of the density fluctuation field that we introduced. So we want to express it as a function of Zn. Sorry, here there is a small typo. It should be B. Sorry for the. Well, the solution is already known. So let me just make a small comment about the solution, the notion of solution. So there was a notion of energy solution for the multi-species systems that was proposed by Bernardin, Funaki, Seturaman. But this is not what we're using. We are really looking at, it's like we reduce our problem to a single species problem, in the sense that we use the notion of solution for the one component in this case. So, and this is also what we are doing here to replace to divide this nonlinear term. So the point here is to so the goal here is to rewrite this term as a function of the field Z, and to do this we employ the second order Boltzmann-Gibbs principle, which was introduced by Patricia and Milton, and it's a result that allows to replace a local. So if you have one conservative stochastic process, you can replace with a controlled error a local function of this quantity by a function of the conserved field, So in particular, a nonlinear function. So what you do is that you replace the occupation a product of the occupation variables on two sides, x and x plus 1, by their right and left average over a box of a finite size. And this you can do with an error which is well controlled. So in the limit for in the n to infinity limit. For the proper choice of the size of the box that you're choosing. So let's analyze in particular the first case, which is the one that gives KBZ and diffusive behavior. So to apply all of these results that are a bit abstract at the moment. So now we have these two linear combinations. We have the sum or the difference of fields. Just let me stress one thing, it can be confusing. So here z minus, I see that it's the sum, but this minus refers to the fact that the velocity is minus e over 3 n to the 3 over 2. And then you have plus because you have positive velocity. So let's analyze the first field. The only thing to look at is the nonlinear term. So if you look at Dinkin's formula for this field, this is the explicit form. So you have a bunch of products of psi A, psi B, etc. So you apply the second order Boltzmann gives by choosing a box of size epsilon n, so macroscopically small. And then so now you can divide all the sum of products of psi A and psi B as a product of two over the left and the right average of psi A and psi B. And so here, if you look at this term in particular, you recognize that here you have the sum of psi A and psi B and the sum of psi A and psi B, but average over the left box and over the right box in X. So, and here you recognize that basically you found the field because here you have a sum of psi A and psi B. So the sum of YA and YB. So once you have this, you can rewrite this term as the product of the field Z minus, so the field that we analyze, evaluated over this I epsilon arrow function, so over the indicator function over boxes of size epsilon around this point. And so basically, once you take the limit for n going to infinity and epsilon going to 0, you can prove that the martingale associated to the dynamics of Z minus converges to the weak solution of the stochastic Burgers equation. So far there is nothing more than what we already saw for WASEP, for one component. What is different is what happens when you look at the second field, so the one that should give the diffusive behavior. So let's give a look at the quadratic term, so the nonlinear term. Well, you see that here you already have you have to play a bit, but then you can reformulate everything in terms of this sum of products of occupation variables. And here you already see that there is an issue because, well, you have a psi A plus psi B, which we can expect will give rise to something of that resembles the form of Z minus, so the other field. And you have psi A minus psi B, which resembles the form of the field Z plus, which is given by the difference of the field in A and B. And so since we expect to have diffusive behavior, so we expect to have non-linear, we expect to have not to have a nonlinear term in the equation, in the limit equation. So we will be in the case of lambda equal to 0. So we expect this term to vanish in the n to infinity limit. And it is what the real further step in the proof of this result of the theorem. So is that what we have to do is we have to show that this integral, so the integral in time of this product of fields, z plus and z minus converges to 0. And to do this, we need to employ a slightly different version of the Boltzmann-Gitt principle.
Alessandra, sorry to interrupt you. We are out of time, so try to make.
So
Sure.
I will just say that. So
Right.
the important novelty of this result is that we were able to show that. So once you reformulate this in terms of the fields z plus and z minus, you obtain a term of this form. So you have the product of field plus and minus evaluated on functions that move. So that move in different frames. So they live in moving frame with different velocity. And the novelty of this result is that we were able to show that this term converges to 0 in the n to infinity limit. And so this is a statement that I wrote here, but actually we can prove it for an arbitrary product of fields and an arbitrary number of velocities. And so we'll skip this technical part. So what we have here, this is the final form of the martingale for the diffusive case. All this term in the second and third line vanish. And we can prove that this converges to the Ornstein-Uhlenbeck equation. And just a remark to end the connection with the mode coupling theory. So this is as far as I know, this is the first model where it was shown formally that the off-diagonal terms of mode coupling matrices are negligible. So proving that the coupling terms of different fields goes to 0 is equivalent to show that the off-diagonal entries of G1 and G2 goes to 0. And that's it. No, okay. Final remarks, but okay, if there is no time, we can conclude here. And if there is any question.
Thank you.
Sorry for going out of time.
Thank you. Very nice talk. Other questions? Okay, either on Zoom or here in the room.
Let me see if there is any.
Zoom. No.
I don't see anything in chat, but.
Well, can you explain your last picture?
Yes. Here.
Yeah.
Yeah. So here is just to say that what we characterize in the. This is what we want to do late after the. So the goal after this obtaining this result. So what we characterize here is what happens here on this dot, whether it is SB, the stochastic Burgers equation, and here on this orange line. So when you have you observe diffusive. So this is the expected behavior of according to the strength of the asymmetry and the scaling. So when you speed up your dynamics of a factor n to the a. And so what we would like to prove later is that, well, we want to characterize what happens on this line. So we know that here there is basically you have Gaussian statistics, you have Ornstein-Uhlenbeck, and what we want to show here is the equivalent for the density field, for the density fluctuation field of what, and for the multi-species model of what Castell and Sarkar obtained for the height function of ASEP. So see if along this line we can characterize the fluctuations in terms of the KPZ fixed point. So it's a huge gap to fill this dotted line, but this is more or less I wanted to present an incomplete picture.
All right, thanks.
You're welcome.
More questions? Also on Zoom?
No, there's nothing on chat as far as I see.
I have one, but okay,
Yes.
I don't know.
No, you have one in chat? No.
No?
Can I ask a question?
Sure, Milton, go ahead.
Yeah, so at the beginning, it's related to Uber question, no? The Uber was saying that in principle, it's difficult it could be difficult to characterize the invariant measures. So does people expect this nonlinear fluctuation hydrodynamic theory to apply for the cases on which you don't really know what the invariant measures look like, or is very important to have somehow explicit or Gibbs sort of invariant measures?
So let's say that to apply all this machinery for the kind of a black box of this nonlinear fluctuating hydrodynamic theory, it is sufficient to know the density current relation at the stationary state. In our case, to apply Boltzmann-Gibbs, it is useful to have an explicit form of the invariant measure. But in principle, even if you don't, so all of this should apply. So the nonlinear fluctuating hydrodynamic theory should apply if you have if you know the hydrodynamic equation and you look at the relation, the current and density relation at stationarity. So even if the environment is not explicit, in principle, yes. So it's if you look at how what you need is actually, you need to know the large time values of your conserved quantities, because you have to expand your field around those values. So yes. Yes. So, and the expression of the mode coupling matrices depends on those values. So yes, you need to know the stationary values. Yes. So yes, now that so I'm not sure if you don't have an explicit form, you can actually, I don't think that you can obtain information about the mode coupling matrices.
Thank you.
You're welcome.
No, here, no one. So Alessandra, I have a question very quickly.
Yes.
What happens if you have more particles per site? Do you have any idea what could happen? I think this is very interesting. Someone should try to look at it.
I guess that in terms of what you can do with mode coupling theory, you should not, as long as quantities are conserved.
Yes, if you allow A, B, right? One should try to see what are the rates. You have these product measures, and then maybe other limits appear, because here it's only KPZ or diffusion, but maybe you start to have these levies.
Yes, you're right, because then you will have that the self-coupling entries will not be zero. Very likely they will not be zero. Yes.
Yeah.
Yes, and then you can, you would observe alpha stable Levy distribution or even modified KPZ, because I think nobody has ever observed a model where there is this modified KPZ. It's really something weird, because I mean it's the same exponent but different scaling function. It's
yeah, but now there is kind of a conjecture what should be the modified KPZ.
Okay.
Okay, but still has not been derived in this setting with the two conservation laws. All right, good, very nice. So this is the last so no more questions, right? Okay, so at least here in the room, no, in chat, no, at Impa, I don't think so. So I think, Claudia, correct me if I'm wrong, but I think this is the last seminar in July, right? So, and we stop. And I think now we are back in September or probably in August. This is something I don't know. Anyway, thank you very much, Alessandra. You finished the whole year of seminars. Thank you so much.
Thank you.
Thank you. Bye.
Bye.
And I will see you in Lisbon in a couple of weeks, more or less.
Yeah, let's hope so. We are expecting 500 people. Oh my God. All right. Thank you. Thank you so much.
Bye-bye.